Welcome to AQA AS 17.1 on Mass Spectroscopy. This is part of the Analytical Techniques topic. If you need to look at your textbook, then it's pages 224 to 225. Now, you have met Mass Spectroscopy before as part of the atomic structure way back in Unit 1, so you may find it useful to go back and have a look at the video for that, or look at your textbook or review your notes so that you're familiar with how we get Mass Spectroscopy to work. And we've always talked about atoms before, so this is mass spectroscopy looking at molecules, so it's slightly more complicated. So our lesson objectives are to understand that high-resolution mass spectrometry can be used to determine the molecular formula of a compound from the accurate mass of the molecular ion. So as I said before, we've always looked at the mass spectra of atoms before, and isotopes, we've not looked at molecules. So in this lesson, we're going to look at some molecules. So the first thing to do is to show you what an actual mass spectra of a molecule looks like. So here's a simple example. We've got an example spectrum for ethanol, which you're all familiar with from your GCSE. So as you can see, it looks more complicated. There's lots more peaks there than there was when we looked at just atoms. So you need to know how to interpret these. So just like before, we've got relative intensity on the y-axis, and we've got m over z, so we've got mass divided by charge, remember, on the x-axis. So if you're looking at this, you should all know that the molecular mass of ethanol is 46, and we can see this on our spectra. And whenever you look at a spectra of a molecule, what you're looking for is the furthest right peak, so the peak on the furthest right. And that will tell you the molecular mass of the molecule that you're looking at. And in this case, you can see it's 46, which we know is true, because if you add up the relative molecular mass of ethanol, it's 46. So we can summarize what the spectra look like on this slide. So what we're interested in at AS is the molecular ion. And a molecular ion is the peak with the highest number. So it's not the tallest peak. It's the peak with the highest number. So it's the peak to the furthest right of the spectra, and it represents the molecular mass. So if we look again at our spectra, you can see that the peak on the far right hand side is not the tallest peak, because the tallest peak is at about 31, but it's the peak to the furthest right, and that shows us that the molecular mass of ethanol is 46. So one of the questions to think about is, why are there so many peaks in the mass spectra of a molecule? And this is because the molecular ion is what forms first of all. So when your molecule goes into your mass spec, and you think of all the things that happen to it that we know from our atomic structure unit, you end up with the molecular ion is just a molecule having lost an electron, so it's got a positive charge. However, that molecular ion is not going to be stable. So what happens, it then fragments, which is a fancy way of saying that it just splits into smaller parts. So the molecule breaks up into smaller bits. Now each of those fragments is going to give a peak in the mass spectra. And every molecule is going to give you a different pattern. So the particular pattern that you get in your mass spectra can be used to identify the molecule. Now we do this in A2. You don't need to worry about it in AS. So once you get into A2, you'll look into how we can use that pattern to identify the molecule, but you don't need to worry about it now. All you need to do for AS is to be able to find the molecular ion peak, which, as we said, is the one to the furthest right, and to understand that we do get many peaks. And that's because the molecular ion fragments into smaller parts. So the only thing left for us to look at is about high-resolution molecular mass, which we've not talked about before. And this is really useful. And high-resolution, as you are aware from previous topics, just means that we're recording it to more decimal places. So as we know, except for carbon, so by definition carbon has got the relative atomic mass of 12, it's going to be a whole number. But all of the other atoms, the relative atomic masses are not going to be whole numbers. So quite often in simple calculations, like when we're calculating molecular mass, we'll round them up to whole numbers. But they're not whole numbers. For example, we talk about oxygen's being 16, but it's actually 15.9949. And we talk about hydrogen as being 1, but it's actually 1.007829. So the reason this is important is because to the nearest whole number, there's many different molecules that might have a given mass. However, they would have different masses to 4 decimal places. So if we had a molecular spectroscopy done on a molecule, so if we had a mass spectrum of a molecule and we only had it to the whole number, so we had a low resolution mass spec, then we wouldn't be able to distinguish between two molecules that have the same molecular mass. But if we have high resolution molecular mass, we can find that to either 3 or 4 decimal places. So if we can do that, we can then distinguish between different molecules that might have the same mass to a whole number, but they'll have different masses if we do it to 4 decimal places or 3 decimal places. So this can be a bit confusing, but so it's best if we look at an example. So if we look at the next slide, so for example here we have two chemicals which would have the same mass to the nearest whole number. So to the nearest whole number they would both have a molecular mass of 46. So you've got C2860, which is a real molecule, that's just ethanol. The mass of the carbon in that would be 24. The mass of the hydrogen would be 6.046974, and the mass of the oxygen would be 15.9949. Now if you add all that together, you get a total mass of 46.0418 to 4 decimal places. Now if you could have C3H10, now that's a completely made up formula, but that would give you the same molecular mass of 46 if you were just doing it to the nearest whole number. However, if we do it to 4 decimal places, then our mass would then be 36 because we've got 3 carbons, but the mass of the hydrogen would then be 10.07829. So if we add those two together and record it to 4 decimal places, that's 46.0782. So we could then take our mass spectra of this molecule, and we could then, if we had a high resolution mass spec, it would give us it 4 decimal places. So it could tell us which of these two we've got. So it could tell us whether we've got C2860 or whether we've got C3H10. So even without looking at the fragmentation pattern, which we'll look at in A2, by looking at high resolution molecular mass, it can give you a bit more information about the molecule. Back to our lesson objectives, which were to understand that high resolution mass spectrometry can be used to determine the molecular formula of a compound from the accurate mass of the molecular ion. So as usual, if you don't feel you've met this objective, then go back and either rewatch the video or look at your textbook to help, or find some other source of information.